In September of 2019, a radio astronomer named Anna Kapinska was sitting at her desk, scrolling through images. Not photographs, not the kind of images you would recognize. These were radio maps, visualizations of electromagnetic emissions at wavelengths invisible to the human eye, captured by one of the most powerful radio telescope arrays ever built. The telescope was called ASCAP, the Australian Square Kilometre Array Pathfinder, a network of 36 radio dishes, each 12 metres across, spread across the remote desert of Western Australia. It was designed to do something no previous radio telescope could do: survey enormous swathes of the sky at once, with a sensitivity to faint, diffuse structures that older instruments had never possessed. The field of view was 30 square degrees, equivalent to the surface area of roughly 150 full moons as seen from Earth. And it was feeding data into a project called EMU, the Evolutionary Map of the Universe, which had a simple and staggering ambition: to increase the total number of known radio sources from roughly 2.5 million, the entire accumulated catalogue of every radio telescope in the history of the discipline, to approximately 70 million in a single survey. Let us begin. Kapinska was browsing the early images from the EMU pilot survey. Not with machine learning, not with artificial intelligence, with her eyes. Old-fashioned, human pattern recognition, the same tool that has driven every major observational discovery in the history of astronomy. And as she scrolled, she noticed something that did not fit. A shape in the data that she could not match to any known type of astronomical object. It was circular, faint, enormous. A ghostly ring of radio emission hanging in deep space like a cosmic smoke ring, billions of light years from Earth, with no visible counterpart at any other wavelength. No optical light, no infrared, no X-ray, nothing. Just radio waves forming a perfect circle in the void. She labelled the image with 2 letters and a question mark. WTF. A few days later, her colleague Emil Lenk found a second one. Then the team found a third, then a fourth, this one in archival data from the giant microwave radio telescope in India, captured in 2013 but never noticed. The objects have been hiding in the data for years. They were real. They were confirmed by multiple telescopes at multiple frequencies, and nobody had any idea what they were. Ray Norris, a professor at Western Sydney University and the leader of the EMU project, had predicted years earlier that the new generation of radio telescopes would discover things that could not be explained by existing theories. He had even coined a term for these anticipated surprises. He called them WTFs. But he did not expect to find one so quickly, and he did not expect it to look like this. A perfect circle of radio emission, 1 million light years across, 20 times the width of the entire Milky Way galaxy, visible only in radio wavelengths, with no known mechanism capable of producing it. Norris and his team gave these objects a formal name. They called them Odd Radio Circles, ORCs. And the name was deliberately understated because the objects themselves are anything but ordinary. As of late 2025, 8 ORCs have been confirmed, with several more candidates under investigation. Each one is a ring of synchrotron radiation, the specific type of electromagnetic emission produced when electrons spiral through magnetic fields at velocities approaching the speed of light. The rings are edge-brightened, meaning the outer boundary glows more intensely than the interior, like a soap bubble illuminated from within. They range in estimated diameter from several 100,000 to over 2 million light years. 2 million light years. Our entire galaxy, the Milky Way, with its 200 billion stars and its 100,000 light-year diameter, could fit inside a single ORC 20 times over. These are among the largest individual structures ever detected in the universe, and they appear to have no business existing. The team's first task was to determine what ORCs are not. They are not supernova remnants. Supernova remnants are typically a few dozen light-years across and are found near the galactic plane, embedded in the disk of their host galaxies. ORCs are hundreds of thousands of light-years wide and exist far from any galactic plane. The scale is wrong by a factor of 10,000. They are not planetary nebulae. They are not the radio lobes of active galactic nuclei, the jets of plasma launched by supermassive black holes. Those structures are elongated and asymmetric. ORCs are almost perfectly circular. They are not Einstein rings, the gravitational lensing effect that bends light from a distant source into a ring shape. Einstein rings require a massive foreground object to act as a lens, and no such object has been found at the centre of any ORC. What the team did find at the centre of some ORCs was unexpected. Galaxies. Specifically, massive elliptical galaxies. 3 of the confirmed ORCs, including ORC1, ORC4, and ORC5, have elliptical galaxies sitting precisely at their geometric centres. The probability of this being a coincidence, of a galaxy randomly landing at the exact centre of a structure 2 million light-years wide, is vanishingly small. The galaxies are connected to the ORCs. They are likely responsible for creating them. But how? 3 hypotheses have been proposed. The first is a merger of supermassive black holes within the central galaxy. When 2 galaxies collide, and their central black holes eventually spiral together and merge, the event releases an extraordinary burst of gravitational and electromagnetic energy. This energy could propagate outward as a spherical shock wave, accelerating electrons in the intergalactic medium and producing a bubble of synchrotron radiation that, seen from our perspective billions of light-years away, would appear as a ring. The second hypothesis is a starburst termination shock. In this scenario, the central galaxy experienced a brief, intense period of star formation, producing millions of new stars in just a few tens of millions of years. The combined stellar winds from these stars, amplified by the supernova explosions that followed as the most massive stars died, pushed a shockwave outward through the intergalactic medium. Over billions of years, this shockwave expanded to the enormous scale we now observe, exciting electrons along its leading edge and producing the characteristic ring of radio emission. The third hypothesis is simpler but harder to confirm. The ORCs may be the end-on view of radio jets from an active galactic nucleus. If we happen to be looking straight down the barrel of a jet, the 2 lobes of radio emission on either side of the galaxy could overlap and appear as a ring, rather than the elongated double structure we usually see. The orientation would have to be precise, but the universe is large, and improbable alignments do occur. None of these hypotheses has been confirmed. None has been ruled out. The data does not yet favour one explanation over another. What the data does tell us is that something happened in those central galaxies, something violent enough to sculpt a structure of radio-emitting plasma larger than anything we have previously encountered. Something that occurred billions of years ago, and whose echo we are only now detecting because our instruments finally became sensitive enough to see it. And ORCs are only the beginning. They are one entry in a growing catalogue of signals arriving from deep space that we did not expect and cannot fully explain. Signals that challenge our models. Signals that reveal structures and processes that the universe has been producing for billions of years while we lack the tools to notice. Some of these signals are bursts of radio energy so brief and so powerful that they release more energy in a millisecond than our sun produces in a year. Some are steady streams of antimatter particles bombarding our planet from a source that remained hidden for decades. Some are patterns in the cosmic microwave background that should not be there if our understanding of the early universe is correct. Before we go further, if you are kind enough, a gentle like and tap on subscribe would mean the world to me. It is a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive. The universe is speaking. It has been speaking for billions of years, in wavelengths we could not hear, through instruments that did not yet exist, from distances so vast that the signals arriving at our detectors today left their sources before the Earth was formed. We are only now beginning to listen properly. And what we are hearing does not match the story we thought we knew. Anna Kopinska labelled her discovery with 2 letters and a question mark. That label, in the language of science, is not an expression of confusion. It is the beginning of understanding. Because the most important discoveries in astronomy have never begun with an answer. They have begun with the honest recognition that something is there that should not be, and the willingness to look at it until it reveals what it is. 8 ghostly circles, each larger than anything we have ever catalogued, hanging in the radio sky like the rings of an explosion whose source we cannot identify. That is what the universe put in front of us in 2019, and we have been trying to understand it ever since. But the circles are not the strangest signal we have received. 800 light-years from Earth, there is something else, something older, something closer, something that has been showering our planet with antimatter for longer than we have existed as a species, and until very recently, we had no idea it was there. In 1972, a small satellite orbiting the Earth detected something it was not designed to find. NASA's second small astronomy satellite, known as SAS-2, was scanning the sky for sources of gamma radiation, the highest energy form of light in the electromagnetic spectrum. Gamma rays are produced by the most violent processes in the universe: supernova explosions, matter spiraling into black holes, collisions between particles accelerated to nearly the speed of light. They are the fingerprints of cosmic violence, and SAS-2 was built to map them. In the data, the satellite recorded an intense source of gamma rays coming from the direction of the constellation Gemini. It was bright, it was persistent, and it had no counterpart at any other wavelength. No optical light, no radio waves, no infrared, nothing. The satellite could see the gamma rays clearly, but the source itself appeared to be invisible. It was radiating energy at the extreme end of the electromagnetic spectrum and doing nothing else, as if something enormously powerful was hiding in plain sight, broadcasting its presence in one frequency while remaining completely silent in every other. The angular resolution of SAS-2 was poor, roughly 2.5 degrees at its operating energy. That meant the satellite could determine only that the source existed somewhere within a relatively large patch of sky, a region containing thousands of stars and multiple other known objects. Identifying which specific object was producing the gamma rays was impossible with the available technology. The source was filed, catalogued, and given a name by Italian physicist Giovanni Bignami, who would spend the next 2 decades of his career trying to find it. He called it Geminga. The name was a contraction of Gemini, gamma ray source. But in Bignami's native Milanese dialect, the word Geminga means something else entirely. It means, it is not there. For 20 years, Geminga remained one of the most frustrating objects in astrophysics. It was the second brightest persistent source of gamma rays in the entire sky, outshone only by the Vela pulsar. 99% of its energy output was in the gamma ray band. It was pouring out radiation with an intensity that demanded explanation, and yet every attempt to identify it at other wavelengths failed. Radio telescopes found nothing. Optical telescopes found nothing. The source was there and not there simultaneously, a paradox that Bignami's pun captured perfectly. The cosmic community knew something extraordinary was hiding in the constellation Gemini. They simply could not find it. The breakthrough came in 1983, when Bignami and his team used the Einstein X-ray satellite to detect a faint X-ray signal from the general direction of Geminga. The signal was weak, far too weak to pinpoint the source precisely, but it narrowed the search area. Then came a longer wait, 8 more years of technological development, of improved instruments, of satellites being designed and launched and aimed at the same patch of sky. And finally, in March of 1991, the answer arrived from 2 separate missions, nearly simultaneously. The German-built ROSAT satellite, an X-ray observatory sensitive enough to resolve individual sources within crowded fields, detected a periodic signal from Geminga's location. The signal pulsed. It repeated with a period of 0.237 seconds, flashing on and off roughly 4.2 times per second with the precision of an atomic clock. Within weeks, the same periodicity was confirmed in gamma rays by the Egret telescope aboard NASA's Compton Gamma Ray Observatory. The X-rays and the gamma rays were pulsing in synchrony. The source was not a cloud, not a nebula, not a distant galaxy. It was a pulsar, a neutron star, the collapsed remnant of a star several times more massive than our Sun, that had exploded as a supernova approximately 300,000 years ago, now spinning on its axis more than 4 times per second, sweeping beams of radiation across the cosmos like a lighthouse built from the corpse of a dead star. But Geminga was not an ordinary pulsar. It was profoundly abnormal in ways that would take years to fully appreciate. The first abnormality was its silence in radio wavelengths. At the time of its identification, every known pulsar in existence had been discovered through radio emissions. Pulsars were, by definition, radio objects. They were found by radio telescopes, catalogued by radio astronomers, and understood through the framework of radio pulse analysis. Geminga broke that definition. It was the first pulsar ever identified that produced no detectable radio pulses. It screamed in gamma rays and whispered in X-rays, but was virtually mute in radio. The radio lighthouse beam, if it existed at all, was either pointed away from Earth or so weak at standard observing frequencies that decades of searching had failed to detect it. The explanation for the radio silence came in 1997, when 3 independent observations from the Pushchino Radio Astronomy Observatory in Russia finally detected extremely faint radio pulses from Geminga. But the pulses were at approximately 100 MHz, far below the frequency range where most radio telescopes had been searching. Standard pulsar surveys focused on frequencies between 430 and 1600 MHz. Geminga was broadcasting below the band that anyone had thought to listen to. It was not truly silent. It had been sending signals for 300,000 years. We simply were not tuned to the right frequency. We were not listening correctly. The second abnormality was Geminga's motion. Using observations from the European Southern Observatory's telescopes in Chile and the Canada-France-Hawaii telescope, Bignami's team discovered that Geminga was moving across the sky at an extraordinary rate, approximately 0.2 arc-seconds per year. For a neutron star 800 light-years away, this translates to a velocity of roughly 210 kilometers per second. The corpse of a dead star, containing 1.5 times the mass of our Sun, compressed into a sphere roughly 20 kilometers in diameter, hurtling through the galaxy at 756,000 kilometers per hour. At that speed, Geminga will cross a distance equal to the apparent diameter of the full moon in just over 10,000 years. In astronomical terms, it is sprinting. The third abnormality was revealed in 2003, when a team led by Patrizia Caraveo used the European Space Agency's XMM Newton X-ray Observatory to discover 2 ghostly tails of X-ray emission streaming behind Geminga as it races through space. The tails stretch 3 trillion kilometers across the sky, trailing behind the pulsar like the wake of a ship cutting through dark water. They are produced by the interaction between Geminga's intense magnetic field, its rapid rotation, and the interstellar medium through which it moves. As the pulsar ploughs forward at 210 kilometers per second, it compresses the gas and magnetic fields ahead of it by a factor of 4, creating a bow shock, a crescent-shaped wave of compressed material in front of the pulsar. Behind the shock, electrons and their antimatter counterparts, positrons, accelerated to extreme energies by the pulsar's spinning magnetic field, spiral outward along the enhanced magnetic field lines and emit X-rays as they go. The result is a pair of luminous tails, visible only in X-ray wavelengths, marking the path of a dead star's passage through the galaxy, like contrails behind a jet aircraft. But the most consequential discovery about Geminga did not come until 2017, and it did not concern the pulsar's structure, or its motion, or its X-ray tails. It concerned what Geminga has been doing to us, to Earth, to every living thing on this planet, for longer than our species has existed. In 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art particle detector mounted on the exterior of the International Space Station, 200 meters above the Earth's surface, was switched on. Among the particles it was designed to detect were positrons, the antimatter counterparts of electrons. Positrons are produced by various cosmic processes, including radioactive decay and cosmic ray interactions with interstellar gas. They were expected to be present in the cosmic ray flux bombarding Earth. What was not expected was the quantity. The alpha magnetic spectrometer detected far more high-energy positrons than any existing model could explain. By 2013, the detector had recorded over 400,000 positrons, the largest sample of cosmic ray positron data ever collected, increasing the world's total cosmic ray positron data by a factor of 100. Something out there was manufacturing antimatter and sending it toward Earth in quantities that defied every prediction. For years, some physicists hoped the excess positrons might be a signature of dark matter annihilation, the theoretical process by which particles of dark matter collide with each other and produce electron-positron pairs. If confirmed, this would have been one of the most important discoveries in the history of physics, the first direct detection of dark matter particles through their annihilation products. The excitement was enormous, the stakes were extraordinary, and the answer, when it finally came, pointed not toward dark matter, but toward the ghost that was not there. In 2017, the High-Altitude Water Cherenkov Gamma Ray Observatory, known as HAWC, located near Puebla, Mexico, detected a small halo of gamma radiation surrounding Geminga. The gamma rays had energies between 5 and 40 trillion electron volts, trillions of times more energetic than visible light. The halo was produced by positrons and electrons accelerated by the pulsar, colliding with starlight and boosting it to gamma ray energies through a process called inverse Compton scattering. Then, in 2019, a team led by astrophysicist Mattia Di Mauro used a decade of data from NASA's Fermi Gamma Ray Space Telescope to reveal the full extent of Geminga's gamma ray halo. It was not small, it was vast. At an energy of 10 billion electron volts, the halo spanned 20 degrees of the sky, roughly the area occupied by the Big Dipper constellation. At lower energies, it was even larger. If human eyes could see gamma rays, Geminga's halo would dominate the night sky, covering an area 40 times larger than the full moon. An invisible cloud of the most energetic light in the universe, surrounding a dead star 800 light-years away, has been hanging over our heads for longer than civilization has existed. Di Mauro's team determined that Geminga alone could be responsible for as much as 20% of the excess high-energy positrons detected by the alpha magnetic spectrometer aboard the International Space Station. 20% from a single pulsar. Extrapolating from that number to the cumulative contribution of all pulsars in the galaxy, the researchers concluded that pulsars are the most likely explanation for the entire positron excess. The antimatter mystery that had consumed a decade of research, that had tantalized physicists with the possibility of dark matter detection, was most likely being caused by the spinning corpses of dead stars scattered across the Milky Way, accelerating particles to relativistic speeds and flinging them into the galaxy in invisible streams of antimatter that bombard every planet, every moon, every asteroid in their path. Geminga is 800 light-years from Earth. It has been radiating gamma rays and producing antimatter for roughly 300,000 years. Its halo, if visible, would be one of the largest structures in our night sky. And until 1972, we did not know it existed. Until 1991, we did not know what it was. Until 2019, we did not know how large its influence extended. A single pulsar, 20 kilometers across, has been showering our planet with antimatter for millennia. And the only reason we discovered this is because we built a particle detector and bolted it to the outside of a space station. What else is out there that we have not yet built the instrument to detect? What other signals have been arriving for thousands or millions of years, passing through our atmosphere, through our bodies, through the ground beneath our feet, completely unnoticed because we have not yet learned to listen at the right frequency, or look at the right wavelength, or build the right detector? Geminga hid for 20 years because we were searching for radio pulses at the wrong frequency. The ORCs hid for decades because our telescopes lacked the sensitivity to detect faint, diffuse radio structures. The positron excess hid for even longer because we had no detector in space capable of counting antimatter particles with sufficient precision. Each discovery was not a discovery of something new, it was a discovery of something that had always been there, waiting for us to develop the ability to perceive it. The universe is not quiet. It has never been quiet. It is saturated with signals, layered on top of each other at every frequency, at every energy, at every scale. From the gamma-ray screams of dead stars to the radio whispers of structures larger than galaxies. We are surrounded by information that we cannot yet read. And every time we build a new instrument, every time we extend our perception into a wavelength or an energy range we could not previously access, we find something we did not expect. Something that was always there. Something that changes what we thought we knew about the universe we live in. The signals are not stopping. They are accumulating. And the next one, the one that arrives from a direction and a wavelength that no current model predicts, may be the one that changes everything. In 2001, the Parkes Radio Telescope in New South Wales, Australia, recorded a pulse. Nobody noticed. The telescope was surveying the region near the Small Magellanic Cloud, one of the Milky Way's satellite galaxies, searching for pulsars. The data was archived, stored on servers, forgotten. 480 hours of recorded sky, filed away like old newspapers in a library basement. The pulse sat inside that archive for 6 years. In 2007, a professor at West Virginia University named Duncan Lorimer assigned an undergraduate student named David Narkovich to search through that archived data. Not for pulsars, for something else. For bright, isolated pulses that might have been missed by the standard search algorithms, which were designed to find repeating signals, not one-off events. Narkovich was looking for needles in a haystack the size of a small country, and he found one. A single burst of radio emission, less than 5 milliseconds long, so bright that it saturated the detector in the primary beam. 30 Janskys of peak flux. For reference, most astronomical radio sources register in the millijansky range, thousandths of a single Jansky. This signal was tens of thousands of times brighter than typical background sources. It flared, peaked, and vanished in less time than it takes a hummingbird to beat its wings once. The burst had a distinctive signature. Its higher frequency components arrived at the telescope before its lower frequency components, a phenomenon called dispersion. When radio waves travel through ionized gas, the free electrons in that gas slow the lower frequencies more than the higher ones. The effect is cumulative. The more gas the signal passes through, the greater the delay between the high and low frequencies. By measuring the amount of dispersion, astronomers can estimate how much ionized material the signal traveled through. And the dispersion of this burst was enormous, far too large to be explained by the gas within our own galaxy. The signal had traveled through the intergalactic medium. It had come from outside the Milky Way. Lorimer's team calculated the distance, roughly 1.5 to 3 billion light-years. The signal had been travelling through the void for longer than complex life has existed on Earth, and it had arrived at our telescope during a routine survey, unnoticed, and sat in a data archive for 6 years before a student scrolling through numbers on a screen realised what it was. The luminosity implied by that distance was staggering. In less than 5 milliseconds, this source had released as much energy in radio waves as our Sun produces in several days. Not over its entire electromagnetic output, just in radio. Whatever produced this burst was converting energy into coherent radio emission with an efficiency and intensity that had no precedent in the observational record. The Lorimer burst, as it came to be called, was roughly 10 to 12 orders of magnitude brighter than any known radio pulse at the time. It was not a pulsar. It was not a rotating radio transient. It was not interference from terrestrial electronics. It was something new, something no existing category could accommodate. And then, for 6 years, almost nothing happened. The astronomical community was skeptical. A single event, detected by a single telescope, found in archival data years after the fact, with no repeat observation to confirm it. Science does not build theories on single data points. Worse, in 2010, a researcher at Swinburne University named Sarah Burke-Spalauer found signals in the same Parkes data that looked superficially similar to the Lorimer burst, but turned out to be interference. Microwave ovens. The staff at the observatory had been opening microwave oven doors before the heating cycle completed, and the escaping radiation had been picked up by the telescope's receivers and recorded in the data as dispersed pulses. These false signals, called peritons, cast a shadow over the Lorimer burst. If microwave ovens could produce signals that mimicked cosmic events, how could anyone be sure the Lorimer burst itself was not some similar artifact? The answer came in 2013, when Dan Thornton, a postgraduate student at the University of Manchester, found 4 more. 4 new bursts, all in Parkes data, all at high galactic latitudes, far from the plane of the Milky Way, all with dispersion measures too large to be explained by galactic electrons. The dispersion of some was nearly 3 times greater than the Lorimer burst, implying distances of 5 to 10 billion light-years. Thornton's team gave the phenomenon its permanent name, fast radio bursts, FRBs. The term stuck, and the field that would grow around it over the next decade would become one of the fastest expanding areas of research in all of astrophysics. As of late 2025, several thousand fast radio bursts have been detected. They arrive from random locations on the sky. They last between a fraction of a millisecond and a few milliseconds. They occur at an estimated rate of several thousand per day across the entire sky. Each one releases as much energy in that fleeting instant as our sun produces in days. Some of them have been traced to galaxies billions of light-years away, and after nearly 2 decades of study, involving hundreds of research teams on every continent, using the most sensitive radio instruments humanity has ever built, we still do not know what causes them. Here is what we do know. The brevity of the burst constrains the size of the source. Light travels approximately 300 kilometers in a millisecond. If the burst lasts 1 millisecond, the emitting region must be smaller than roughly 300 kilometers across. Otherwise, different parts of the source would emit at different times, and the burst would be smeared out, stretched over a longer duration than a millisecond. The coherence of the signal, the fact that the burst arrives as a sharp, well-defined pulse rather than a diffuse wash of radiation, requires that the entire emitting region fire essentially simultaneously. This means the object producing these bursts is compact, extremely compact, a few hundred kilometers or less. In a universe filled with structures spanning millions of light-years, the most powerful radio events ever recorded are being produced by something smaller than a mid-sized asteroid. The energy is the other constraint that narrows the field. Producing that much coherent radio emission in a millisecond requires a mechanism that converts energy into radio waves with extraordinary efficiency. The mechanism must be coherent, meaning the electrons producing the radiation must be organized, synchronized, emitting in phase with each other the way a laser produces light. Incoherent thermal radiation, the kind emitted by hot gas or stellar surfaces, cannot produce the brightness temperatures implied by fast radio bursts. The numbers are beyond comprehension. The brightness temperature of a typical FRB, the temperature a thermal source would need to reach in order to produce the same intensity of radiation, exceeds 10 to the 35th Kelvin. That number has no physical meaning as an actual temperature. No object in the universe is that hot. It is a mathematical marker indicating that the radiation cannot be thermal. It must be coherent. Something is organizing the electrons with a precision that produces radio emission billions of times more intense than any thermal process could achieve. There is exactly one category of known astrophysical object that is compact enough, energetic enough, and magnetically violent enough to satisfy both constraints: neutron stars, specifically magnetars. Neutron stars with magnetic fields so intense that they warp the structure of the star itself. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. A magnetar has a magnetic field roughly 1,000 times stronger than that, a quadrillion times stronger than the planet you are standing on. At the surface of a magnetar, the magnetic field is so powerful that it distorts the shape of atoms, stretching them into elongated cylinders aligned with the field lines. It alters the way light propagates, splitting photons into different polarization states and bending their paths. It stores energy in twisted field configurations that can release suddenly, catastrophically, in events called starquakes, when the crust of the neutron star fractures under magnetic stress and the field lines snap into a new configuration, releasing their stored energy in a burst of radiation that can be detected across the observable universe. The connection between magnetars and fast radio bursts moved from theoretical speculation to observational fact on the 28th of April 2020. On that date, two telescopes simultaneously detected a burst from a magnetar within our own galaxy. The magnetar was designated SGR 1935+2154, located roughly 30,000 light-years away in the constellation Vulpecula. The CHIME telescope in Canada and the STARE-2 array in the United States both recorded a bright radio burst from the magnetar's direction, coincident with a burst of X-rays detected by orbiting satellites. The radio burst was brief. It was dispersed. It had the spectral characteristics of a fast radio burst, and it came from a known magnetar that had been observed erupting in X-rays and gamma rays for years. It was, technically, the first fast radio burst ever detected from within the Milky Way, and it established, beyond reasonable debate, that magnetars can produce fast radio bursts. But here is the complication that keeps the field from declaring the mystery solved. The burst from SGR 1935+2154 was bright by galactic standards, but faint by extragalactic standards. It was roughly 1,000 times less energetic than the weakest fast radio bursts detected from other galaxies. If the same burst had occurred in a galaxy a billion light-years away, no existing telescope would have detected it. It would have been too dim. The fast radio bursts we detect from cosmological distances are far more powerful than anything the Milky Way's known magnetars have been observed to produce. So while magnetars can produce FRB-like bursts, the magnetar mechanism as currently understood does not obviously scale up to explain the most luminous events in the catalogue. Something about the most powerful fast radio bursts requires either a more extreme version of a magnetar than we have observed in our galaxy, or a fundamentally different mechanism, or an environment that amplifies the burst energy in ways we do not yet understand. And then there are the repeaters. Most fast radio bursts appear to be one-off events, a single burst from a single location never repeated. But roughly 4% of known FRB sources have been observed to produce multiple bursts. These repeating sources behave differently from the apparent one-offs in several ways. Their individual bursts tend to be broader in frequency, more complex in structure, and more variable in duration. Some repeaters are extraordinarily prolific. FRB 20001-2102A, the first repeating source ever identified, discovered at the Arecibo Observatory in 2012, has produced thousands of detected bursts across multiple telescopes and frequency bands. It is located in a dwarf galaxy roughly 3 billion light-years from Earth, embedded in an extreme magneto-ionic environment that imprints a distinctive rotation measure on its signal. FRB 20,220,912A, discovered by CHIME in 2022, reached observed burst rates of up to 390 per hour during its peak activity, contributing a measurable fraction of the total all-sky FRB rate all by itself. A single source, somewhere in a galaxy 400 million light-years away, was screaming so loudly and so frequently that it briefly rivaled the combined output of every other FRB source in the observable sky. The existence of repeaters tells us something important. Whatever produces these bursts, at least in some cases, survives the event. It is not destroyed. It is not consumed. It bursts, recovers, and bursts again, sometimes within milliseconds, sometimes after weeks of silence. The mechanism is not a one-time catastrophe like a collision or an explosion. It is a recurring process driven by a source that persists. This is consistent with a magnetar model, where starquakes and magnetic reconnection events can repeat over the lifetime of the star. But the sheer rate of repetition in the most active sources pushes the energetics to the edge of what magnetar models can comfortably accommodate. Some analyses have questioned whether even the total magnetic energy stored in a magnetar's field is sufficient to power the cumulative radio output observed from the most prolific repeaters. And in January of 2025, a discovery arrived that fractured the emerging consensus even further. The CHIME telescope detected a repeating fast radio burst designated FRB 20,240,209A. The team traced the burst to its source. It was not in a star-forming galaxy. It was not near a region of active stellar birth, where massive stars die young and leave behind magnetars. It was at the extreme outskirts of a massive, ancient elliptical galaxy, a dead galaxy. A galaxy where star formation had ceased billions of years ago. The burst originated roughly 130,000 light-years from the galaxy's center, in a region where almost no stars exist. The most energetic radio events in the universe were coming from the emptiest, quietest neighborhood in one of the oldest, most quiescent galaxies ever associated with a fast radio burst. This should not happen under the standard model. If fast radio bursts come from magnetars, and magnetars form when massive stars explode as supernovae, then fast radio bursts should be found in galaxies where massive stars are being born and dying, young galaxies, active galaxies, star-forming galaxies, not 11 billion-year-old elliptical galaxies, where the last supernova occurred billions of years before the burst was detected. The researchers proposed that the source might reside in a globular cluster, a dense, spherical collection of ancient stars, where exotic interactions between compact remnants, white dwarfs collapsing, neutron stars merging, could produce a magnetar through a delayed formation pathway, rather than a direct supernova. If confirmed, it would mean that the universe has more than one way to build the engines behind fast radio bursts. That the phenomenon is not tied to a single formation mechanism, that the cosmic scream can originate from sources as diverse as the youngest stellar nurseries and the oldest stellar graveyards. There is a number that captures the scale of what we are dealing with. Several thousand fast radio bursts per day, across the entire sky, every day. Most of them go undetected because no telescope happens to be pointing at the right patch of sky at the right millisecond. We catch only a tiny fraction. The ones we do catch arrive from galaxies spanning the entire observable universe, out to distances of 8 billion light-years and possibly beyond. Each one carries information not only about its source, but about every atom of ionized gas it passed through on its journey to our telescope. The dispersion measure of a fast radio burst is a direct measurement of the total column density of free electrons between the source and the detector. This means that every FRB is a probe, a cosmic ruler, a measuring stick that stretches from its home galaxy to ours and counts every free electron in between. In 2020, a team led by J.P. McCart used a sample of localized fast radio bursts to demonstrate that their dispersion measures follow a relationship predicted by cosmological models of the intergalactic medium. By measuring the dispersion of FRBs at known distances, the team effectively weighed the gas between galaxies and confirmed that the total amount of ordinary matter in the universe matches the predictions of Big Bang nucleosynthesis and cosmic microwave background observations. They found the missing baryons. For decades, astronomers had known that the amount of normal matter they could directly observe, in stars, in galaxies, in hot gas clusters, accounted for only about half the total amount predicted by the standard cosmological model. The other half was out there somewhere, too diffuse and too cool to detect with conventional methods. FRBs found it. The missing matter was in the intergalactic medium, spread thinly through the vast voids between galaxies, too sparse to emit or absorb enough radiation to be detected by any telescope, but dense enough to imprint its presence on the dispersion of radio bursts passing through it. A phenomenon we do not understand, produced by sources we cannot identify, travelling through a medium we could not previously measure, solved a problem that had persisted for 2 decades. The scream told us what the silence could not, and still the bursts keep coming. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, detects 2 to 3 fast radio bursts per day and is currently undergoing upgrades that will allow it to pinpoint burst locations with unprecedented precision. The Square Kilometre Array, a massive radio observatory spanning sites in Australia and South Africa, is being built with the explicit capability to detect and localize fast radio bursts at rates and sensitivities far exceeding any current instrument. Every new telescope sensitive to the radio sky is finding FRBs, Every new survey reveals sources that push the boundaries of what existing models can explain. The catalogue grows, the patterns emerge, the exceptions multiply as fast as the confirmations. Something is producing the most powerful, coherent radio events in the observable universe. It does so from compact regions smaller than a city. It does so from sources scattered across billions of light years. It does so in bursts so brief that they are over before the light from the beginning of the burst has travelled the width of a large island. Some sources do it once and never again. Some do it hundreds of times per hour. Some do it from the violent nurseries of newborn stars. Some do it from the quiet outskirts of galaxies that stopped forming stars before our sun existed. And the total rate of these events across the full sky is thousands per day, every day. The universe is screaming, in millisecond bursts that carry more energy than our star produces in days, from billions of light years away, through a medium that encodes the weight of all the matter between here and there. And we have been listening for less than 20 years. The ghost in Gemini showed us that a single dead star could shower our planet with antimatter for 300,000 years without our knowledge. The odd radio circles showed us that explosions larger than galaxies could hide in the radio sky for decades until our instruments became sensitive enough to see them. And the fast radio bursts are showing us something perhaps more unsettling than either, that the universe is full of voices we are only now learning to hear. That the loudest scream in the cosmos lasts less time than a blink, and that the question of what is producing it is still, after thousands of detections and hundreds of papers and decades of effort, fundamentally open. The signals from the first two chapters were unexpected, but ultimately traceable. ORCs led us to central galaxies and shockwaves. Geminga led us to a known class of object behaving in unknown ways. Fast radio bursts lead us to the edge of a cliff. The data is accumulating faster than the explanations. The models are straining under the weight of exceptions, and every new telescope that comes online finds something that the previous generation could not have predicted. The catalogue of unexplained signals is not shrinking, it is growing, and the pattern that connects them, if there is one, is beginning to suggest something that no individual signal could convey alone. That our instruments are not discovering anomalies in an otherwise well-understood universe. They are revealing that the universe we thought we understood was a simplified sketch drawn from incomplete data. And the real portrait, the one being assembled burst by burst and ring by ring and halo by halo, is vastly more complex, more active, and more strange than the sketch ever suggested. There is a habit in science that serves the discipline well under normal circumstances, but fails catastrophically at moments of genuine revolution. The habit is specialization. The radio astronomer who discovered the odd radio circles does not attend the same conferences as the particle physicist, analyzing positron data from the alpha magnetic spectrometer. The team studying Geminga's gamma-ray halo does not share a departmental hallway with the team cataloguing fast radio bursts. The researchers modelling the cosmic microwave background anomalies do not typically read papers about synchrotron emission from intergalactic shockwaves. Each discovery exists in its own literature, its own funding stream, its own community of experts. Each signal is studied in isolation, and the pattern that connects them, if anyone were to step back far enough to see it, has no name, because no single discipline owns it. Step back now. Look at everything we have examined across the first 3 chapters. Not at the details, at the shape. In 2019, a new generation of radio telescopes with unprecedented sensitivity to faint, diffuse structures revealed enormous rings of synchrotron radiation hanging in deep space. Structures up to 2 million light-years across, invisible at every wavelength except radio, produced by mechanisms that 3 competing hypotheses cannot yet distinguish between. The odd radio circles had been there for billions of years. We found them only when our instruments became capable of detecting them. Before ASCAP and its phased array feeds, the ORCs did not exist in our catalogue of the universe. After ASCAP, they did. The universe did not change. Our ability to perceive it did. 800 light-years from Earth, a dead star the size of a city has been showering our planet with antimatter for 300,000 years. Geminga was invisible to radio telescopes because it broadcasts at frequencies below the band that anyone thought to search. It was invisible to optical telescopes because it emits almost nothing in visible light. Its gamma-ray halo, large enough to dominate the night sky if our eyes could see it, went undetected until 2017 because no instrument with sufficient sensitivity and angular resolution had been pointed at it for long enough. The positron excess it helps explain was not even measurable until we bolted a particle detector to the outside of a space station. The antimatter was always arriving, the gamma rays were always there, we simply had no way to know. And from every direction in the sky, thousands of times per day, bursts of radio energy lasting less than the blink of an eye arrive from sources scattered across the observable universe. Each one carries the energy output of days of solar radiation compressed into a millisecond. We have detected thousands. We have traced roughly 100 to their host galaxies. We have identified one source within our own galaxy and linked it to a magnetar. And after nearly 2 decades of study, the fundamental question of what produces the majority of these bursts remains unanswered. Every new discovery narrows the possibilities and simultaneously introduces new exceptions. The fast radio bursts from dead galaxies, the repeaters with burst rates that strain the energy budgets of magnetar models, the sources that fire once and vanish forever. Each exception is a data point. Each data point is a signal, and the signals are accumulating faster than the theories. Now add the signals we have not yet discussed, because the catalogue of unexplained cosmic transmissions does not end with ORCs, Geminga, and FRBs. It extends in every direction, at every wavelength, across every energy scale. In the constellation Eridanus, in the southern celestial hemisphere, there is a patch of the cosmic microwave background that is colder than it should be. The CMB cold spot spans roughly 5 degrees of sky, more than 10 times the apparent diameter of the full moon. It is approximately 70 millionths of a degree Kelvin colder than the average CMB temperature, which itself is only 2.725 Kelvin above absolute zero. 70 millionths of a degree, that sounds trivial. It is not. The cosmic microwave background is the most precisely measured radiation field in the history of physics. Its temperature is uniform across the entire sky to a precision of roughly 1 part in 100,000. The variations that do exist, the hot and cold spots that encode the density fluctuations of the infant universe 380,000 years after the Big Bang, follow a specific statistical distribution predicted by the standard cosmological model. The cold spot does not fit that distribution. It is too large, too cold, and too statistically improbable to be comfortably explained as a random fluctuation. The probability of finding a deviation this extreme in a Gaussian random field that matches the standard model has been estimated at less than 2%. Multiple explanations have been proposed. The leading conventional hypothesis involves a supervoid, an enormous underdense region in the large-scale structure of the universe, lying along the line of sight to the cold spot. As CMB photons travel through this void, they lose a small amount of energy due to the accelerating expansion of the universe, a phenomenon called the integrated Sachs-Wolf effect. The Dark Energy Survey has confirmed that such a void exists in the direction of the cold spot, roughly 1 billion light-years across, one of the largest underdense regions ever identified. But detailed calculations show that the supervoid alone cannot account for the full temperature deficit. It explains some of the coldness, not all of it. The gap remains. More recent studies, published in 2023 and 2024, have identified an alternative possibility. A statistically significant correlation between the positions of nearby spiral galaxies and cold spots in the CMB suggests the existence of a previously unknown foreground component, a systematic temperature decrement around local galaxies that could imprint patterns on the CMB we have been interpreting as primordial. The Eridanus supergroup, the largest complex of spiral-rich galaxy groups in the local universe, sits precisely in the cold spot region. If this foreground effect is real, it would mean that part of what we have been reading as a signal from the birth of the universe is actually a signal from much closer, much more recent structures contaminating the ancient light. We have been misreading the message. confusing the foreground for the background, mistaking a nearby whisper for a primordial shout. And then there is the signal that sits below the death line. In 2023, the Murchison Wide Field Array in Western Australia detected an object designated GPMJ 1839-10. It emits radio pulses every 21 minutes and 58 seconds. The pulses last between 30 seconds and 5 minutes. The signal has been present in archival data stretching back to 1988. 35 years of consistent periodic radio emission from a source roughly 15,000 light-years away in the constellation Scutum. The problem is not that the signal exists. The problem is that it should not. If the source is a neutron star, as the polarization properties of the signal strongly suggest, then its rotation period places it far below the theoretical death line. The death line is the boundary in parameter space below which a neutron star's combination of magnetic field strength and rotation rate is insufficient to power the pair production cascades that generate coherent radio emission. A neutron star rotating once every 22 minutes should be radio silent. Its magnetic field should be too weak relative to its rotation to accelerate particles to the energies required for emission. And yet, GPMJ 1839-10 has been broadcasting for at least 35 years with remarkable stability, its rotation period unchanged to within fractions of a millisecond over that entire span. A magnetar starquake could temporarily reignite emission from a dead pulsar, but starquakes dissipate within years, not decades. A highly magnetized white dwarf could rotate this slowly, but no known white dwarf produces radio emission at this luminosity. A binary system involving a white dwarf and a companion star was proposed in early 2026, with the pulsing arising not from rotation, but from the magnetic axis periodically sweeping through the companion's stellar wind. The community remains divided. No explanation accounts for all the observed properties simultaneously. The signal continues, every 22 minutes, from a source that our best models say should be silent. Each of these phenomena, individually, is a puzzle, an anomaly, a question mark in the margin of an otherwise coherent textbook. The cold spot is a curiosity in cosmology. GPMJ 1839-10 is a challenge to pulsar physics. ORCs are a mystery in extragalactic radio astronomy. Geminga's positron halo is a problem in high-energy astrophysics. Fast radio bursts are an unsolved question in transient astronomy. Individually, each one is manageable, a single loose thread in an otherwise intact fabric. But look at the threads together. Count them. Notice the direction they are pulling. Every one of these signals was discovered not because we went looking for it, but because a new instrument, operating at a sensitivity or wavelength or energy range that no previous instrument could access, revealed something that was already there. Not something new, something old. Something that had been broadcasting, radiating, pulsing, or glowing for thousands or millions or billions of years before we developed the capacity to detect it. The universe did not suddenly start producing odd radio circles in 2019. It did not begin generating fast radio bursts in 2007. Geminga did not start emitting positrons when we launched the alpha magnetic spectrometer. The cold spot did not appear when WMAP began operating. These signals predate not only our instruments, but in many cases, our species. They have been part of the fabric of the cosmos for longer than complex life has existed on Earth. And we found them only in the last few years, some of them in the last few months. This is the pattern that nobody named. The pattern is not in the signals themselves, it is in the timing, in the sequence, in the accelerating rate at which our instruments are revealing phenomena that existing models did not predict and cannot yet fully explain. Every generation of telescopes has discovered things the previous generation could not see. That is expected. That is the normal progression of observational science. What is not normal is the ratio. The fraction of new discoveries that fall outside existing theoretical frameworks is not shrinking as our models improve, it is growing. We are not converging on a complete picture of the universe, we are diverging from one. Every new instrument opens a window into a sky that is more complex, more active, and more saturated with unexplained signals than the models suggested it would be. Consider the history. In the 1950s and 60s, radio astronomy revealed quasars, pulsars, and the cosmic microwave background. Each discovery required new physics. Each was eventually incorporated into the standard model, expanding it, deepening it, making it more complete. In the 1990s and 2000s, X-ray and gamma-ray observatories revealed magnetars, gamma-ray bursts, and the accelerating expansion of the universe. Again, new physics was required. Again, the models expanded. But in each of these earlier eras, the number of genuinely unexplained phenomena at any given time was small, a handful, manageable. The rate of discovery was paced by the rate at which new instruments came online, and the theoretical community could keep up. The questions were answered, one by one, within years or decades. Now look at the present. ORCs, discovered in 2019, still unexplained. Fast radio bursts, discovered in 2007, source mechanism still debated after nearly 2 decades. The CMB cold spot, identified in 2004, still anomalous after 20 years of analysis. Long-period radio transients below the death line, discovered in 2022 and 2023, still defying theoretical explanation. Geminga's full positron contribution, measured only in 2019, still reshaping our understanding of cosmic ray physics. The catalogue is not closing, it is opening. And the instruments that are coming online in the next decade, the Square Kilometre Array, CMBS-4, the next generation of gravitational wave detectors, the Vera C. Rubin Observatory, will observe the sky at sensitivities and resolutions that exceed current capabilities by orders of magnitude. If the pattern holds, if every significant improvement in instrumental capability reveals new, unexplained phenomena at a rate that exceeds the theoretical community's capacity to explain them, then we are not approaching the end of discovery. We are approaching the beginning of a different kind of problem. A problem of abundance. A universe that contains more signals than we have theories to account for, more structure than our models predict, more activity than the textbooks describe. The honest conclusion is not that we are close to understanding the universe. The honest conclusion is that we are close to understanding how little we understand. The signals we have catalogued in these chapters are not anomalies in an otherwise complete picture. They are the first visible fragments of a picture we have not yet learned to see. Each new telescope is a new eye, and every time we open a new eye, the universe looks less like the simplified diagram we carry in our heads, and more like something vast and detailed and humming with processes we have not named. The odd radio circles tell us that the intergalactic medium is shaped by events of extraordinary violence that leave no trace at any wavelength except radio. Geminga tells us that the space around us is saturated with high-energy particles produced by dead stars we cannot see. Fast radio bursts tell us that the most energetic, coherent radio events in the cosmos are produced by sources smaller than a city, from mechanisms that our best models can approximate but not confirm. The cold spot tells us that either the large-scale structure of the universe is imprinting unexpected patterns on the oldest light in existence, or that we are misreading the CMB in ways we have not yet corrected for. And the long-period transients tell us that even the objects we thought we understood best, neutron stars, can behave in ways that violate the theoretical boundaries we drew around them. Put them together, what do they say? They say the universe is noisier than we thought, more active, more structured, more layered with overlapping signals at every wavelength and every energy. They say our instruments have been too blunt, too narrow, too limited to hear most of what is being broadcast. They say the silence we perceived was not silence at all, it was deafness. And now that we are beginning to hear, what we are hearing is not a single message, it is a cacophony, a symphony of processes operating at scales from 20 kilometers to 2 million light-years, at energies from radio waves to gamma rays, at durations from a fraction of a millisecond to billions of years. All happening at once, all layered on top of each other, all arriving at our detectors simultaneously, requiring us to sort signal from signal from signal in a universe that apparently does nothing quietly. This is not the universe of the textbook. The textbook universe is orderly. Stars are born, they burn, they die. Galaxies rotate smoothly. The cosmic microwave background is a clean, Gaussian random field with well-understood statistics. Pulsars obey death lines. Radio sources are either known categories or noise. That universe is a first draft, a sketch made from the data available when the textbook was written. The data arriving now, from instruments that would have seemed impossible a generation ago, is drawing a different picture. A picture in which the sketch was not wrong. It was incomplete. Dramatically, fundamentally, structurally incomplete. And the parts that were missing are not minor details in the margins. They are entire categories of phenomena that we did not know existed. In the final chapter, we step back further still, past the individual signals, past the pattern of accelerating discovery, past the instruments and the models and the data, to the question that sits beneath all of it, the question that every unexplained signal, every anomalous data point, every phenomenon that refuses to fit the existing framework is quietly, persistently, relentlessly asking. What if the universe we thought we were living in is not the universe we are actually living in? What if the real cosmos, the one that has been broadcasting its nature at every wavelength for 14 billion years, is something we have barely begun to perceive? And what does it mean to be a species that has just, in the last blink of cosmic time, opened its first real eyes? There is a moment in the development of every sensory organ, in every species that has ever evolved the capacity to perceive its environment, when the organ begins to function, but the brain behind it has not yet learned to interpret the input. A newborn human opens its eyes for the first time and sees light. Not shapes, not depth, not faces. Light. A wash of undifferentiated brightness flooding a visual cortex that has no framework for organizing what it is receiving. The hardware is online, the software is not. Interpretation comes later, pattern recognition comes later, understanding comes later. First, there is only the raw, overwhelming, unprocessed flood of signal. That is where we are. We built the eyes, we pointed them at the sky, and what came flooding in was not the orderly cosmos we had prepared ourselves to see. It was a wall of signal. Radio circles the size of galaxy clusters, antimatter raining from invisible dead stars, millisecond screams carrying the energy of suns from billions of light years away, cold spots in the oldest light in the universe that do not match the models, pulsing sources that defy the theoretical boundaries we drew to define what should and should not be possible. All of it arriving simultaneously, all of it layered on top of each other, all of it demanding interpretation from a species that built its first radio telescope less than a century ago. 1 century. That is the span of time during which humanity has been able to hear the universe in radio wavelengths. Before Carl Jansky's rotating antenna detected radio emissions from the Milky Way in 1932, the radio sky did not exist for us. It was there. It had been there for 13.8 billion years. Every pulsar that has ever spun, every magnetar that has ever erupted, every fast radio burst that has ever fired, every synchrotron electron that has ever spiraled through a magnetic field, all of it was broadcasting. The universe was saturated with radio signal from the moment the first stars ignited and the first magnetic fields formed. And for the entirety of human history up to that point, we heard none of it. We lived inside a symphony and perceived silence. Now multiply that by every wavelength we have learned to detect since. X-rays, discovered as an astronomical tool in the 1960s. Gamma rays, mapped from orbit beginning in the 1970s. Gravitational waves, first detected in 2015. Neutrinos from astrophysical sources, confirmed in 2017. Each new channel opened a flood of information that had been propagating through the cosmos for billions of years, passing through our planet, through our bodies, through the walls of our homes, completely unnoticed. The gravitational wave from 2 merging black holes a billion light-years away stretched and compressed every atom in your body by a fraction of a proton's width as it passed through, and you felt nothing. The neutrinos from a supernova in a distant galaxy passed through the Earth at nearly the speed of light, trillions of them threading through every square centimetre of the planet's surface every second, and not one of them disturbed a single atom on its way through. The gamma rays from Geminga's halo have been arriving at the top of our atmosphere for 300,000 years, and the first human to know they existed was born in the 20th century. We are not observers who arrived late to a quiet universe. We are listeners who were deaf and have only just begun to hear. And the universe we are hearing is not quiet. It never was. The quietness was in us. Think about what that means for the question we carry with us every time we look up. The question that sits beneath every signal chapter, every anomaly, every unexplained burst and ring and halo. Are we alone? The question assumes that if intelligent life existed elsewhere in the universe, we would have detected its signals by now. That is the foundation of the Fermi paradox. If they are out there, where are they? The logic seems sound. We have been listening for decades. We have built increasingly sensitive instruments. We have scanned millions of star systems for narrowband signals, and we have found nothing confirmed. But look at what else we failed to detect during those same decades. We failed to detect odd radio circles, structures millions of light years across, until 2019. We failed to detect the full extent of Geminga's positron halo until 2019. We failed to detect fast radio bursts until 2007, and they occur thousands of times per day at energies that exceed the daily output of our Sun. We failed to detect long-period radio transients below the death line until 2022. We failed to detect gravitational waves until 2015, despite the fact that merging black holes have been warping space-time for billions of years. In every case, the signal was there. The signal had always been there. We were not listening at the right frequency, or with the right sensitivity, or at the right time, or with the right instrument. If we missed the loudest natural signals in the universe for decades because our instruments were not tuned correctly, what confidence can we place in the claim that the absence of detected artificial signals means the absence of artificial signal sources? The answer is very little. We have been listening for extraterrestrial intelligence with instruments that, until very recently, could not even detect the natural phenomena occurring in our own galactic neighbourhood. We were searching for whispers while standing inside a thunderstorm we could not hear. This is not an argument that extraterrestrial intelligence exists. It is an argument that we are not yet in a position to meaningfully claim it does not. The absence of evidence, in a search conducted with instruments we now know were blind to entire categories of astrophysical phenomena happening right next door, is not evidence of absence. It is evidence of the limitations of the search. And those limitations are not behind us. They are still with us. The instruments coming online in the next decade will be more sensitive than anything we have today, by factors of 10, 100, 1,000. If the pattern of the last 2 decades holds, those instruments will reveal phenomena we have not predicted, signals we are not expecting, structure we did not know was there. And among those signals, in that flood of new data from a universe we are only beginning to perceive in its full complexity, there may be something that is not natural, something that carries the hallmark of intention, something that, when we finally develop the right instrument, tuned to the right frequency, pointed at the right patch of sky, at the right millisecond, will be unmistakable. Or there may not. The universe may be exactly as empty of intelligent signal as it appears. The silence may be real. We may be the first, or the only, or the last. That possibility is as real as any other. But the honest assessment of our current position is not that we have searched thoroughly and found nothing. It is that we have barely begun to search, with instruments that have proven inadequate to detect even the most energetic natural phenomena in our immediate cosmic environment. And we are drawing conclusions from that inadequate search about the existence or non-existence of signals we have not defined, from sources we cannot predict, at frequencies we may not yet have the technology to detect. Humility is not a common posture in science. The enterprise runs on confidence, on the conviction that the models are close enough, the data is sufficient, the framework is sound. That confidence has earned extraordinary results. It put humans on the moon. It predicted the Higgs boson. It imaged the shadow of a black hole. But confidence applied to questions we are not yet equipped to answer becomes something else. it becomes premature closure. It becomes the assumption that because we have looked and not found, there is nothing to find. And the history we have traced in these chapters, the history of signals that were always there but required new eyes to see, should give us pause before we close any question permanently. The universe has been speaking for 14 billion years. It speaks in radio waves and gamma rays, in gravitational waves and neutrino streams, in cosmic rays and antimatter showers, in the thermal whisper of the oldest light in existence and the millisecond shrieks of dying magnetic fields. It speaks in rings of synchrotron radiation 1 million light-years wide and in cold spots imprinted on the afterglow of creation. It speaks continuously, at every frequency, in every direction, with an eloquence that requires no audience and acknowledges no listener. And we, on a small rocky planet orbiting an ordinary star in the suburbs of a barred spiral galaxy, have spent the last 93 years building ears. Imperfect ears. Narrow ears. Ears that can hear 1 octave of a symphony that spans the entire electromagnetic spectrum and beyond. Ears that miss most of what is being said because they are tuned to the wrong band, or aimed at the wrong patch of sky, or not sensitive enough to pick up the faintest signals, or not fast enough to catch the briefest ones. We are listening to the universe through a keyhole, and what we hear through that keyhole has already overthrown our expectations, filled our journals with anomalies, and revealed that the cosmos is more complex, more active, and more saturated with unexplained phenomena than anyone anticipated. What will we hear when we open the door? Anna Kapinska wrote 2 letters and a question mark on an image of something no human had ever seen before. WTF. That moment, that honest, unguarded, unscientific response to something genuinely new, captures something essential about where we stand. Not at the end of discovery, not at the point where the catalogue is nearly complete and only a few loose ends remain. At the beginning. At the moment when the instruments have become just barely powerful enough to reveal that the sky we thought we knew is a pale sketch of the sky that actually exists. Every signal in these chapters is a reminder that the universe does not wait for us to be ready. It broadcasts whether we are listening or not. It produces phenomena at every scale and every energy, whether we have instruments to detect them or not. It does not simplify itself to match our models. It does not limit its complexity to what our current generation of telescopes can resolve. The signals are not stopping. They are not slowing. They are not becoming more predictable as our instruments improve. They are doing the opposite. They are revealing a cosmos that is wilder, noisier, more structured, more layered, and more deeply strange than any generation of astronomers has previously encountered. The rings are in the radio sky. The antimatter is in the particle data. The screams are in the millisecond bursts. The anomalies are in the oldest light in existence. The impossible pulsars are below the death line, and the explanations, the theories, the models, the frameworks that will eventually make sense of all of it have not been written yet. Somewhere, right now, a telescope is recording data that contains a signal no one has noticed. It is sitting in an archive, on a server, in a file that a student has not yet opened. It may be a ring, it may be a burst, it may be a periodicity that no model predicts. It may be something we do not have a name for. It will be found the way all the others were found. Not by an algorithm, not by a theory. By a pair of human eyes scrolling through data, noticing something that does not fit, and having the courage to label it honestly. The universe is speaking. It has always been speaking. The only question that matters now is whether we are willing to keep building better ears, keep opening new windows, keep listening at frequencies we have not tried, and keep admitting, every time we find something we cannot explain, that the 2 most honest letters in science are the ones Anna Kapinska wrote on that image in 2019. WTF. And then, keep listening.